Hello, everyone, and welcome to the first installment of this YouTube channel's astronomy series for beginners. And I would actually like to kick this series off by starting with a more mathematical concept that may not appear to have a direct relation with the field of astronomy, but it definitely is an important analysis, I should say. It is an important analysis for some future topics that we will discuss, like Kepler's laws, or maybe even, orbits, and so on. So let's actually begin with this video on ellipses. And just to preface this video, I would like to point out, not point out, I would like to say that this is my first video on this channel where I'm properly researching, properly editing, properly presenting this video. So the quality may not be very nice of this video, but I definitely hope to grow this skill as each video as each video keeps getting uploaded. Okay, so with that in mind, let's actually get started with ellipses. So first thing to keep in mind is that an ellipse is actually a type of conic section, and if you wanted a dedicated video on all the four general conic sections, you can let me know in the comment section below. Right, so we know about circles, right? Circles are probably one of the most common objects in our day-to-day lives, maybe even when you're looking at mathematical problems, or if you're looking at, I don't know, circles are definitely very common. So the most distinctive property of a circle is that the distance from the center of a circle to any point on its circumference, that's a constant value, and we've even termed that as the radius. So a circle is actually a special case of an ellipse, and we will see how exactly we have how exactly we say that a circle is a special case of an ellipse. But what you know about an ellipse is that it's a conic section, and it kind of looks like a circle, like an elongated circle, like a short and fat circle in a sense. It and now it does not follow this property of the circle, that the distance from the center of the ellipse to any point on the boundary or the circumference of the ellipse, that value is not constant. It keeps changing for different points on the boundary. Okay, so unlike a circle, the distance from the center to everywhere else is not the same. And what we need to know, this is the starting introductory part of some special terms of an ellipse. So now, because we have asserted the fact that the distance from the center of an ellipse to every other point on the ellipse is not a constant value, therefore we must therefore it stands to reason that there are two distinct diameters, with different values, right? And now that we have two different quantities of different values, one of these diameters must be greater than the other, and obviously the other one must be lesser than the other one. And so we've given these two diameters distinct names, right? So the longer diameter in length, we call that the major axis of the ellipse, and the and can you guess what we call the shorter diameter? Yeah, that's the minor axis. If you got that correct, please pat yourself on the back. Anyway, so now so generally by convention we define the length of the major axis as 2a and the length of the minor axis as 2b, and then by extension we say that the semi-major axis is the longer radius, and the semi-minor axis is the smaller radius, the shorter radius. Okay, so and then we obviously we represent the semi-major axis with A and semi-minor axis with B. Right. So now I'm going to define particular equations of the ellipse, and different how to derive some special features of an ellipse, like the vertexes and co-vertexes and so on. So for all of these properties that I'm going to discuss of the ellipse, I'm going to make one key assumption, and that assumption is that I'm assuming a sort of short and fat ellipse. That is okay. So now when I say that x square by a square plus y square by b square is equals to 1, that doesn't always mean that the semi-major axis always has to be along the x-axis, right? You can also define an ellipse with an equation of x square by 9 plus y square by 25, and that would still be a perfectly normal, perfectly applicable ellipse. Okay, I mean there's no problem in saying that. Just for the sake of generality, we have written that x square by a square plus y square by b square is equal to 1. But if you put if y square if the term under y square has a greater value than the term under x square, you don't have to freak out, right? Anyway, so now remember how I talked about how a circle was a special case of an ellipse, right? So let's actually look at that. Okay, so there is actually a term that we define called the eccentricity of the ellipse, and it has a specific formula, root over of 1 minus b square by upon a square, right? So 1 minus b square upon a square. So 1 is separate and the minus b square by a square is separate, and the root of that particular expression. So how does the eccentricity help us, right? The eccentricity is actually a measure of sorts. So it's a measure of how flat or how round the ellipse is, how flat or round that particular ellipse is. And the eccentricity can take values between 0 and 1, right? And so the ellipse, sorry, a circle, the special case of the ellipse which we were talking about, it has an eccentricity of 0, right? Because remember how I said that the semi major axis is the smaller diameter and the semi minor axis, sorry, larger radius, sorry, the larger radius, and the semi minor axis was the smaller shorter radius, right? So semi major axis is the longer radius, and the semi minor axis is the shorter radius. So in a circle, since there is the radius is the same, I mean since the distance from the center to every point on the circumference is the same, thereby the value of a and b become equal to one another. So when we write that down in our ellipse eccentricity equation, we get 1 minus b square by a, 1 minus b square by a square root, but b square and a square are equal to one another, so that just becomes 1. So you get root over of 1 minus 1 root over of 0, and that's just 0. So we basically say that an ellipse of eccentricity 0 is basically a circle. That's how the circle becomes a special case of an ellipse. And the eccentricity can take values between 0 and 1, to keep that in mind, for if we use eccentricity, if we use ellipses in the future. And now we will discuss some finer features of an ellipse. So these include the vertex, covertex, the foci, latus rectum, how to find the focuses of the ellipse, right? So let's just discuss that right now. Okay. So when we discussed the major axis and minor axis, we know that the major axis actually joins two opposite points of the ellipse, and so does the minor axis, like diametrically opposite points to one another. So the two diametrically opposite points that are joined to one another by the means of the major axis, we call these the vertices of the ellipse, right? So the major axis connects the vertices of the ellipse, and when we apply that concept to the minor axis, then the minor axis connects the co-vertices of the ellipse. So the diametrically opposite points to one another on the minor axis are called the co-vertices, and the diametrically opposite points on the major axis are called the vertices. Now we will discuss the focuses or the foci of the ellipses, and these foci contain possibly some of the most fascinating properties, one of the most fascinating properties of an ellipse, and this really reveals the beauty of ellipses. Through the foci we get to see the true beauty of ellipses. I mean, it's a mind-boggling property that we're going to discuss. And actually, this property of the foci that we're about to discuss, first we will discuss actually what they are. But when we find out this property of the foci, many people use that as an actual definition of ellipses. Okay, so let's first talk about what are the foci of an ellipse, right? So when we look at an ellipse, right, there are two particular points on that ellipse, on the major axis, by the way. There are two particular points on the major axis of that ellipse which are symmetric about the origin. And well, that while that's cool in itself, what makes these 2 points even cooler is that if you take the sum of the distances of any random point P on the circumference of that ellipse. So just imagine an ellipse, and just take any random point P on one of on the circumference of the circle. Just take any random point P. Okay, so when you take the distance from so these 2 points are on opposite sides of the origin, and they're both on the major axis. So take the distance. So if you sum the distances between these 2 points and that point P, so if you take the sum of the distances from the first focus to that point P and the second focus to that point P, the sum of those distances will always become equal to the major axis, 2 times A. Take any point on the circumference of the ellipse, any point possible. Just take any point possible and measure the distance between the first focus and the second focus and that point, and just sum their distances. And also, because you know that the equation of an ellipse gives you the value of A, sum those distances and then compare that to the value of 2A. They will be equal in all cases. And this is perhaps the most fascinating property of ellipses. And this property is so unique and fascinating that this is one of the definitions of an ellipse. If you go on Google and search ellipses, I mean, I'm not sure, but you will definitely find a certain definition that defines ellipses as that particular conic section where the two focuses, when summed to the distance of any random point, I mean, when the two foci of that conic section, and if you take any random point on the circumference and you sum the distances between that point and the two foci, and that answer will always be equal to twice the major axis. People define an ellipse using that particular definition itself, rather than calling it a conic section where the distance between the center and any point is not equal, and circle is a special case of an ellipse. Not everyone defines it like that. This is also used as a proper definition of the foci of an ellipse, of ellipses itself. That's how fascinating the property is. And now, one thing someone might ask is, how do I find the foci of an ellipse? And we will get to that just right now itself. So the foci, right? So the foci of an ellipse, finding that value, you need to first find this value defined as f. Okay, defined as f, and f is going to be equal to the square root of a square minus b square, where a square and b square still mean semi-major and semi-minor axis. So you will take their squares difference, so a square minus b square, and then square root that. This gives you a value called f. Some people call it c as well. Wikipedia calls it c. I'm calling it f because foci, has some relation. It will be much easier to remember. So the value of the foci will be, the x coordinates will be plus and minus c, because remember, a square minus b square gives you f, and then plus f will be the first focus and minus f will be the second focus. Okay, so the coordinates of the foci will be x coordinate is either plus c or minus c, and the y coordinate is 0. So that is how you find the foci. Once again, to recap, first you find the value of root over of a square minus b square. That is the length of the semi-major axis is square minus the length of semi-minor axis square. You find the square root of that, and then the x coordinates of the foci become plus and minus that value, and the y coordinate becomes 0. Okay, now we will look at one more property, or one more what can we say, one more feature of an ellipse, which is called the lattice rectum of the ellipse. So the lattice rectum has a very simple definition, and it is the two lines on that ellipse about which the ellipse is entirely symmetrical. And one special thing about the lattice rectum is that it is perpendicular to the major axis and both the foci. Okay, so and the length of that lattice rectum will be twice the semi-minor axis upon the semi-major axis. Okay, now we will talk about two very important topics: the parametric form of an ellipse and the tangents to an ellipse. So these are actually two highly mathematical concepts, so let's actually delve into them, and deriving them is not that difficult. It's actually quite easy. So first of all, we know that in a general equation of an ellipse we have x square by a square plus y square by b square is equal to 1. But here we have and we know that the x and y coordinates of this ellipse are connected through that equation. But what if I want to represent a point on that ellipse with just a single parameter to make life easier for me, to represent a point on an ellipse with just one single parameter, because x square by a square plus y square by b square, I want to make my life simple, and I want to have a single I want to have a single parameter that helps me find the relation, that helps me find a point on the ellipse. Okay, so now in the equation of an ellipse we see a something square by some plus something square is equal to 1. X by a is whole, because x square by a square, so I'm just saying x upon a is whole square plus y upon b is whole square is equal to 1. Now I'm assuming you have read trigonometry before, so have you seen any sort of formula in trigonometry where something's square plus another thing's square is equals to 1? Just think about it for 2 seconds. Take your time. You can pause the video, because that is the key idea here. Yes, sine square theta plus cos square theta is equal to 1. That is one of the basic identities, most trivial identities of trigonometry, which almost every person who has read trigonometry is expected to know. So why don't I represent that equation of an ellipse in terms of sine and cos? Because sine square plus cos square is equals to 1, and that equation of an ellipse is already something square plus something square equal to 1, right? So what I'm going to do is I'm going to replace that x upon a term with cos theta, and the y upon b term with sine theta, because that still holds, right? If I say that, it's not wrong, because cos square plus sine square is still equal to 1, and x by a whole square plus y by b whole square is also equal to 1, right? And since because since usually cos theta is used to represent the x-axis in polar forms, that's why we substitute x by a with cos theta and not sine theta, and that's also why we represent y by b with sine theta and not cos theta, right? So then we say that, now I'm just going to take the a and b over to the other side. Then I say that x is equals to a cos theta and y is equals to b sine theta, right? So now we have a single parameter theta to represent this equation. So now here is the now here we get into the misconception part. Okay, now what do people think? Okay, now that we've got this ellipse and we've got a point, any point on the ellipse, I'm going to say that x is equals to a cos theta and y is equals to a sine theta. That is not correct. That is not the correct thing to do. Why is that? because when you join the center to that point and you call x as a cos theta, there is also an a sin theta component, because now that you're breaking that into its components, that line into cos and sine components, you have named an a cos theta component, fine, but there is also an a sine theta in that exists on the ellipse, which we haven't taken care of. We've only defined x as a cos theta and y as b sine theta. We haven't defined y as a sine theta. I mean, we haven't said, and we neither have we called x as b. This thing, neither have we used any term of b to define x, and we haven't used any term of a to define y. So now what do? We're stuck in a dilemma, right? We've said that x is equals to a cos theta and y is equals to b sine theta quite clearly, because we are trying to reduce it to one parameter, right? But when we actually get to using this parameter on the ellipse, we run into a problem, because we get now two components of a and two components of b, a cos theta, a sine theta, and b sine theta, b cos theta. But a sine theta and b cos theta respectively are of no use to us because they don't belong in the parameters. I mean, we have not defined them in the sense that they are not useful to us in the parametric form. So how do we deal with this problem? So we sort of tweak the definition here, and we actually create a circle around the ellipse, which has an equation of x square plus y square is equals to a square, where a is that radius of that circle. That's the general, if you don't know, that's the general definition, equation of a circle on at this, which is centered at the origin. X square plus y square is equals to radius square, and since we are producing a circle around the ellipse with the radius equal to a, we then define the equation of it as x square plus y square equal to a square. And this circle is called the auxiliary circle of the ellipse. Now, how does constructing this help us in finding the parametric form? It's because we define theta using the auxiliary circle. So when we were defining theta with respect to the angle made by the point on the ellipse with the horizontal, then that was causing us problems with the different components of a and b that were being formed. But when we define theta with respect to the auxiliary circle, that is the angle made by the line joining the center of the auxiliary circle to the boundary of the auxiliary circle with the horizontal, then we don't run into any problems. We then have, then it becomes just fine. We have a cos theta comma b sine theta, and now so then we get our proper, no problems, no issues, anything. So then now we will discuss tangents to an ellipse. So let's just take, for there to be a tangent to anything, it needs to just graze or just touch that particular, like a tangent to a circle, for example. We define a tangent to a circle as a limiting case of the secant, because that touches the circle at just one point and then it goes on. So similarly, if we want any line to be a tangent to an ellipse, the same way that there is a tangent to a circle, then how do we define that? So let's just take any random straight line, and we know the equation of a straight line is mx plus c. So now remember that equation, that very simple equation of the ellipse, x square by a square plus y square by b square is equals to 1. Now since y is equals to mx plus c, let me actually replace y square with mx plus c. So we get a square by x square by a square plus mx plus c's whole square by b square equals to 1. So now this part will require a lot of manipulation and whatnot, but basically what we will do from here on is we will get a quadratic in x, which will be x square b square plus x square into, we get a quadratic in x, that is x square, the coefficient of x square will be b square plus a square m square, coefficient of x becomes 2m a square c, and then the constant term becomes a square into c square minus b square, and that's equal to 0. This is a quadratic in x. Now for tangency, the discriminant of that equation needs to be equal to 0. So then you equate 2mca squares whole square with 4 times the coefficients of x square and the constant term. Then you get that final relation. Now that final relation is the one that's more important to us, and we get that c square. Now remember, c was that constant slope intercept term. C square needs to be equal to b square plus a square m square. So if this equation is satisfied, then that line becomes a tangent to the ellipse. Okay, so that is it for today's video. I know that this was not a very great video in terms of explaining or quality and sorts. I was also fumbling quite a bit during the video, I noticed. But this is just my first video, and I hope to get better with this sort of thing as videos go on. This is definitely something I'm very new to, speaking to a camera, microphone, and explaining something to whoever sees this video in the future. So just once again, if you have actually stayed through to this part of the video, I really thank you. I really appreciate the support, and hopefully seeing you for the next video. Okay, thank you.